Hi, this is 5.07 Equilibrium. Chemical equilibrium, the dynamic balance of reactants and products, is a key concept in chemistry. And so hopefully you notice the word part, the equi or equal, as in equal. In any closed system, a chemical reaction will result in a dynamic, ongoing balance between products and reactants. In other words, we don't just have the reactants turn into the products, boom, you're done. They can actually go back and forth. This lesson describes what chemical equilibrium is and how it can be achieved. Goals for this lesson: define the term reversible reaction, describe chemical equilibrium, explain the equilibrium constant, calculate an equilibrium constant expression for a reaction. Chemical reactions are reversible. They may proceed forward. Again, in chemical equilibrium, they may proceed backwards and are described by the equilibrium constant. So your student guide is on slide 2. And from the student guide, I just kept the beginning, the goals, and our keywords. Chemical equilibrium, the process by which the reactants form products and products form reactants at equal rates. So in other words, it's going back and forth. Equilibrium constant is the ratio between the concentrations of the products and the concentration of the reactants. And a reversible reaction is a reaction in which there's a dynamic or moving equilibrium between products and reactants. And hopefully you also see the word reverse, and meaning that it can go backwards and forwards. Equilibrium, or think of it as being balanced. Equilibrium can be discussed in terms of chemical reactions. Considering the following reaction. One hydrogen molecule containing 2 hydrogen atoms, so in other words, dihydride gas plus chloride gas, yields 2 hydrogen chlorides, also as a gas. When this reaction occurs, the reaction goes almost all the way to the right. That is, the reaction favors the products, or in other words, that's the way it's going to go. You're going to take the hydrogen and the chlorine and make HCl. However, a small amount of the HCl product actually breaks down into the reactants in the reverse reaction. Such reactants are called reversible reactions. So in other words, usually we say the hydrogen and the chlorine make the HCl, but the HCl, some of it goes backwards and splits and becomes Cl2 and H2. And that's shown by this double-sided arrow. So this double-sided arrow says it can go forwards and backwards. Although the system at rest is 99% HCl, there is a dynamic situation in which the amounts of reactants and products have achieved a balance. So there is still a little bit back and forth. Hydrogen chloride. This reaction produces a gas that, when dissolved in water, produces hydrochloric acid. HCl liquid is widely used in industry. Alright, so I added our equation here and reminded that a double-sided arrow shows the reactants turn into products, but the reverse, products turn back into reactants, also occurs. Therefore, this is a reversible reaction. The reaction goes almost all the way to the right. In other words, going to the right is a fancy way of saying it's turning into the products over here on the right-hand side. So it is almost completely products made. However, that small amount of HCl product actually breaks back down into the reactants in a reverse reaction. So it is going back and forth. Although 99% of the stuff in the beaker is HCl, 1% is H2Cl2. And then that HCl2 is going to turn back into HCl. And some of the other HCl is going to break it down into H2Cl2. And it keeps going around in a circle. So that's what they mean by dynamic. It's not like you hit this point and everything just stops moving. No, remember the molecules are always bouncing around. So this is constantly happening. It's just that when we say it's at equilibrium, we say even though it's always happening, about 99% is the HCl and about 1% at any time is H2 and Cl2. Reversible reactions occur when the products of a reaction reform into the reactants. Considering the following equation, 2 nitrogen dioxides yields dinitrogen tetraoxide, or N2O4, or nitrogen dioxide gas, which is produced in automobile exhaust, is converted into dihydrogen tetraoxide gas, N2O4. If you placed nitrogen dioxide gas in a closed container, you would expect that at some point the entire container would turn into the N2O4. But that doesn't happen. The reason is that some of the N2O4 reverts to NO2 in a reversible reaction. So in other words, just another example of that really the arrow is pointing both ways. Most of it's turning into N2O4, but because molecules are always moving, some of them break back apart into two molecules of NO2. Products and reactants convert into each other, though one side of the equation is favored over the other. So I feel like we should add what that means. So favored, okay, if the reaction favors to the right, what do you have more of? You have more product. If it favors to the left, what do you have more of? More reactants. Chemical equilibrium is achieved when concentrations of reactants and products remain constant. Okay, so remember how I said that at any time, 99% of what's in the beaker is HCl and 1% is the H2 and the Cl2? Okay, that's what they mean by it's at equilibrium. It's kind of like it's hit this point where it's balanced, everybody's happy, even though things are still converting back and forth. We know that at any point we should have basically 99% of the product. A dynamic interaction occurs in chemical reactions. The term chemical equilibrium denotes that a chemical reaction exists as a dynamic, stable movement between products and reactants. So in other words, dynamic, it's moving back and forth. You're creating products, you're creating reactants, but it's at a constant or stable amount. So it's 99% product, 1% reactant. The term does not imply that the ratio of products to reactants is 1-to-1, because right, that would be 50-50, 50%, 50%, and the example I've been using is 99 to 1%. In fact, equilibrium exists in some reactions where the ratio of products to reactants is 1,000,000 to 1. Equilibrium means that there exists a reversible reaction that over time remains in balance, as shown in the graph of the following reaction. So dihydride plus diiodide yields 2 molecules of hydrogen, monoiodide, but there shouldn't be 2 vowels. So hydrogen, yeah, I think you do, monoiodide. All right, so concentration in capital M, remember that's molar or moles per liter. We have it over time. As time passes, the amount of both reactants and products levels off and becomes stable. So we start out here, we have a lot of the reactants. It changes into products, and then it levels off. We don't have any products to start out with. Pretty soon we have a lot of products, and then it levels off. Now if you notice, they're doing some math here. You have your change in time over your change in concentration of HI, your change in concentration of H2 over your change of time. So again, you can actually figure out some slope and use that mathematical information as well. So I just added a note to chemical equilibrium. This does not mean a 1-to-1 or 50% to 50% ratio. It means that even though reactants are constantly turning into products, and vice versa, products are turning into reactants due to the constant motion of atoms and molecules, the overall percentage of reactants and products stays the same. So 99% HCl, 1% of the H2 and Cl2. A reaction at chemical equilibrium can be graphed. One way to visualize equilibrium is to make a graph that compares the concentration of reactants and products over time. When you consider an equilibrium reaction graphically, keep 2 points in mind. Number 1, a reaction reaches equilibrium when the net or total concentration of the reactants and products stop changing. 2, the concentrations of reactants and products do not need to be equal for equilibrium to occur. So remember I said equilibrium, it has basically the word equal in it. Well, it means equilibrium balance or equal over time, so it stays the same or constant. Note that in a graph like this, equilibrium amounts need not be equal. So reactant A, maybe that was the H2, we have this much. Reactant B, maybe that's the Cl2, we'll have this much. And our product, the HCl, has that much. So again, when the line flattens off, that means what? it means you've reached equilibrium. So I just added the graph to our notes, and reminder, equilibrium has been reached when the graph flattens, or in other words, the amounts do not change. The concentration of the products and reactants at equilibrium in a reversible reaction can be expressed with the equilibrium constant. The equilibrium constant, which is abbreviated K sub EQ. So K just stands for a constant in math, and the sub EQ means that you're talking specifically about the equilibrium constant. So the equilibrium constant, or K sub EQ, gives information about the equilibrium concentrations of reactants and products. Each reaction has a value of K sub EQ for any specific temperature. The equation for determining the equilibrium constant is shown here, where A and B are the reactants, C and D are the products, and A, B, C, D are the coefficients of the compound. All right, so consider the general reaction. So, in other words, we have our chemicals. Chemicals capital A, capital B, do a double displacement reaction or a single replacement reaction, and they change into chemicals C, capital D. The lowercase a, lowercase b, lowercase c, lowercase d are the coefficients. So how you figure out the equilibrium constant is by you take the chemical and you take it to the power of its coefficient. Or it's sometimes useful to think of that it's the concentration of products over concentration of reactions. Thinking about it this way will help you identify general trends and get a feel for what the K sub EQ means. So I like starting off with this first. It's the concentration of your products over reactants. All right, so copy down about the equilibrium constant. Sorry, I zoomed in here so we could see it all. K sub EQ gives information about the equilibrium concentrations of reactants and products. Each reaction has a value of K sub EQ for any specific temperature. So you can either say it's the concentration of products over reactants. Remember, whenever you see the brackets, you read it as the concentration of. Or if you like this format, it shows you here. Or if this is a little bit confusing, what it's saying is that it's the concentration of chemical A to the power of its coefficient times the concentration of chemical B times to the power of its coefficient. Likewise. So, in other words, if I had a chemical equation such as 2H2 plus O2 yields 2H2O, go ahead and try writing the KEQ. So hit pause if you think you got it. If not, let's break it down. So what goes on the top? The products goes on the top. All right, so our product is H2O. So I would write the concentration of H2O to what power? Well, it would be to the power of 2. Because of this x, because of that coefficient right there, that number becomes the exponent. Okay? And then what would go on the bottom? So if you didn't hit pause before, go ahead and hit pause now and see if you can finish it on your own. If you can't, that's okay. This is the first time you're seeing it, and we are practicing. And so now on the bottom goes my concentration of my reactants. All right, so I have both of these. I'm going to just put those on the bottom and write concentration of. And then we're going to multiply. So you can put the multiplication sign. You do not have to, but you can. And then we'll have the concentration of both. Now, which one of those two gets an exponent? Well, there's a 2 right there. And because there's a 2 right there, it's going to have an exponent of 2. All right, if you got that on your own, great job. If not, not a big deal. Don't worry, there'll be more practice. And we'll get that practice in part 2 of this lesson.